This is a video explanation to help you with the start of Packet 2. So Packet 1 was all about finding the area between curves, and that created a two-dimensional shape. Now we want to actually go three-dimensionally. So notice here we have the equation y equals x squared minus 4x plus 5, and that's what's shaded in green right here. And we could find the area underneath this curve just by doing an integral. But what I want you to think about now is we want to take this shape and start to rotate the entire shape around the x-axis. That means if you can visualize it, we're going to end up with a shape that looks like this. For those of you having difficulty visualizing this, let me see if this helps. Here's our curve, x squared minus 4x plus 5 right here. And we're looking to rotate the entire area under this curve. So it's not colored in here, but it's this area right here. We're looking to rotate around the x-axis. So visually, here we go, right? We're starting to rotate around the x-axis. Right, we're about halfway done, and there's a full rotation. It makes a solid three-dimensional shape. It almost looks like a solid candlestick holder. For those of you that want a different example, here is something that might be a little bit more visually easy to understand. It's a different graph. This one is 1/2 sine of 2x plus 1. Right, so this blue area is the area under the curve. And that's what we want to rotate around the x-axis to give us a three-dimensional shape. Right, so let me come down here and start to rotate it. Right about now, you start to see, right, the rotation has started to go around the x-axis, right, and it's creating that solid shape. And there's a full rotation, so I now have a full solid shape. This looks sort of like a vase, a solid vase that is filled in. Hopefully that gives you a little bit of a better idea of creating a three-dimensional shape by rotating around the x-axis. So back to our problem of how do we find the volume of this three-dimensional shape that's created when we rotate this around the x-axis. Well, instead of looking at the entire shape being rotated around the x-axis, let's think about just one thin strip, right? If I take this thin strip right here and rotate this around the x-axis, what will happen? What shape will be created? Right? It might be, I don't know if you can see it there, but really, what you are creating when you rotate that thin strip is a disc or a cylinder. Right, so I have a cylinder here, and what's the volume of a cylinder? Well, that's equal to pi r squared times h, where your radius is right here, and your height really is the thickness of that disc. Well, how does that compare to what we're doing when we're looking at our function? Well, our radius, right, that's right here, and that's the same thing as what value, right? That is our y value. So we could have y squared in here. The pi will stay the same, and our height now, I don't know if you can see it, but our height is really the thickness of this disc, right? And what can we use that as an expression? Well, we really want that thickness to be as thin as possible because we want to put many, many, many discs in there, so that we want our x, or the change in x, to be very small, right? So that we actually can call dx. Our height will be our change in x, because we don't want to just put one disc in there. We really want to take a strip here, a strip here, a strip here, a a strip here. Those will each create disks, so that we're going to have a disk here, a disk here, here, and if you notice right here, I've really only put 1, 2, 3, 4, 5. I want to put as many strips in here to create disks that I would stack on top of one another. Similar to this picture right here, right? Where here you can see multiple disks that if we stack them on top of each other would create this shape. And we're talking about our volume being pi y squared or f of x squared dx. But how many dx's or how many disks do we want to put in there? We want the limit as the number of disks goes to infinity, and hopefully that sounds like an integral, right? So really the formula for finding the volume created by rotating a shape around the x-axis is adding up all those disks, but that's equal to the integral from a to b, whatever your endpoints are, of pi times y squared, because that's our radius, times dx, or another way of looking at that, instead of using y, we can use f of x squared. And if we continue to apply that to our problem, right, remember, here is our original graph, right, of x squared minus 4x plus 5, and we wanted to go between 1 and 4. The formula we're going to use would then give us the integral from 1 to 4 of pi, our y value, but again, instead of putting y or f of x, we actually want to write that function in there, and we're going to square it times dx. And now you really have solved this problem, right? This is the setup and the answer to the problem. Now you just need to actually do the calculus and solve that. You want to square your function out. So there we're squaring the function out, right? Algebraically, yes, it's a little bit tricky. And then you're going to go ahead and take the integral of each of those terms and substitute in 4, and then subtract substituting in 1. And for this geometrical three-dimensional shape, remember this was our function, and when we rotate it around the x-axis, right, I can't remember, we called it maybe a solid candlestick. We got a volume of 78 pi over 5, and that really is in units cubed because it is volume. Now go ahead and look through the rest of this packet and go ahead and try the problems.